Well, thank you very much. Very interesting, very informative. I have a quick question. I understand that with the architecture will be the same for deep learning or HPC. But the problem we're facing these days is a lot of HPC shops cannot make use of the tensor part. They can make use of the CUDA cores, but not the, and that's understandable, right? To make those HPC application use the tensor part, there are a lot of things there too. So is there any way that NVIDIA could disable, let's say, the tensor part for HPC customers on the firmware and to reduce the cost? Because a lot of, as I said, a lot of HPC customers do not want to pay for the tensor part.
Sure.
It's very expensive.
That's more of a marketing question since I don't control what the price is. So even if I gave you a discount, it wouldn't matter because my word doesn't matter. Typically what we're seeing HPC customers use the tensor cores for is not for replacing part of the existing workflows, but for doing things like qualification of uncertainty or application steering. That doesn't answer your specific question. I think it would be pretty hard to disable the tensor cores in the same way it's pretty hard to disable like 32-bit math because it's not something it's not like a discrete IP block that sits on the chip. It is interwoven into the SM, but noted.
So I have a question maybe for all the panel members that you might be able to help us with something that internally our team is struggling with. And that is, how should we define a sustained exascale? For example, would LinPack work okay for doing so? Of course, we get a lot of feedback that may not be the best. But for your world or what you're doing, how would you recommend us having a definition for what we call an actual sustained exascale? We're tracking very carefully what a peak is, which is more straightforward. But the bridge between peak and a sustain is something we're struggling with.
I can answer since I'm standing. So the DOE has a specific definition in mind of how they're defining their exascale system as a multiple relative to a pre-exascale system. So as long as it's 50 times faster than this thing they already have, that's an exaflop. Let's all go home. I understand. I've been heavily involved in HPL for quite a while. For years, I did most of the GPU HPL runs. It's a metric. It's whether it's representative. I don't think it's representative of everything, but the alternatives aren't representative either. There was a lot of work into high performance conjugate gradient. And if you kind of plotted, HPL is completely bound on flops, and high performance gradient was completely bound on memory. And generally it's true that most apps are usually bound on one or the other, but different apps in your workload tend to be bound by different parameters. I don't have a great, other than let's get the exascale thing over with and just move on. I don't have a great answer for you because it doesn't. I would much rather find an answer that involved doing real science, and I struggle to, other than doing it relative to what your existing workload is. There's not just a general. This is a quanta of science, and here's an exaquanta.
Yeah, I'll comment on that as well. Though this is my comment, I'm not representing Intel from my comment. But I'm not a big fan of LinPack myself as a performance measurement for sustained performance, primarily because, and I think as the other speaker was talking about, it really doesn't give you a broad spectrum of true application performance. And there are other benchmarks that are probably better, which was also mentioned, HPCG, is probably a much better benchmark to use to actually say, what is sustained performance that you'll actually see at the application level, as opposed to some ginned up benchmark that just shows, some pure high-speed performance that you'll never see when you really hook up a real application workload. So, that's my statement on it, so.
A question for Dale. So long-term, what role do you see for CPUs?
Every time we sell a GPU, we sell a CPU someplace. Not our CPU, but.
But no, you know what I'm asking. So where do you think CPUs are going to be long-term superior?
I don't think CPUs go away, certainly. We view it as acceleration as parallel optimized and latency optimized. And for a lot of architectural reasons, it's a lot easier for us to build a really great parallel optimized, throughput optimized accelerator if we know that there's a really well latency optimized CPU someplace in the mix. It frees us to do things that you wouldn't want your processor to do if it was, say, in charge of receiving interrupts for network traffic or running an OS. But it unchains us to get a lot more parallel performance out of that silicon area. So we see it complementary. I think that I don't know where the ratio ends up. I think that one of the advantages of acceleration is you can sites that need to can populate very few GPUs per CPU. Sites that have the other different needs can attach a lot of GPUs to one or two CPUs. It just depends on what maps best to your applications.
All right, thank you.
We sell them both, so I think they'll both be around. I was going to go back to your the sustained exascale comment, just make an observation, and it's probably heresy for this room because I'm not a big fan of LINPACK either, but it's just, in some respects, I think it's the simplicity of the number, particularly for funding agencies that look at those, that they want to see that. So I don't see any way of getting around it. One thing I'd encourage you to look at, though, some of the other people mentioned some of the other benchmarks, but starting to look at things like sustained usability of a large system. These large systems, we run LINPACK on them, and then we do that. But then as far as sustained usability, I'm sure University of Arizona and the other guys could all comment on the fact that that's a huge factor in the cost. As far as the CPU GPU question, that's one of the things that we wrestle with, and that's just going to be code dependent. I guess I'll look forward, and I just see the balance thing being the thing that the issue that we've got to wrestle with.
Yeah, I guess I would kind of, I haven't said anything. So yeah, if we redefine LINPACK to be something lower flops, it's going to take that much longer to get there, right? So you can't take a step back, right? The politicians will get angry. But yeah, I really like with regard to CPU, GPU, and really other accelerator mixes, being able to mix and match different combinations for different deployments, I think is quite powerful. And I do like the cloud version of that as well, right? Which is if you aggregated a large number of resources into one cloud infrastructure, even a distributed infrastructure, you don't need to go buy, a 6 GPU to one system and then go buy a 4 GPU to one system. If you start to run things in cloud infrastructure, you'll just deploy on the appropriate combination of resources. And so as people aggregate data centers into mega data centers or hyperscale data centers, then they can contain the appropriate combinations, and you just go to the right spot. So I think there's a lot of flexibility we have going forward there.
On the CPU comment, GPU standpoint, I'm more of a fan of the CPU, which is probably not a surprise coming from Intel. I do believe that the CPU does provide most customers the best return on their investment because it's general purpose. It runs all codes. Most codes are well tuned already. And so therefore, if you're going to build a machine, it just makes sense if you wanted to have that machine running all the time. You can make use of all those resources as opposed to maybe offloading to an accelerator occasionally and not utilizing all your resources. So I think from a standpoint, there are applications where an accelerator makes sense, but I think in general, the CPU is the better place to run high-performance workloads.
Could I ask one quick follow-up question? Where do you think FPGAs fit into this mix? Because nobody's mentioned them.
Well, I think FPGAs do land somewhere. We have quite a few customers that are looking at making use of FPGAs today in high-performance computing systems for unique algorithms that they want to tune or change often in their compute facilities. So I do believe that FPGAs have a place to play. I don't see them as being predominant, but again, there is always going to be somewhere where, especially if you're doing edge compute, where you have a lot of data coming in, you need to filter out that data, the data that's spurious and not relevant. Great place for FPGAs would be that edge, pass on the real data that needs to be done from the compute standpoint. So,
I just still think there's a programmability issue with them. Programmability, and I think that's going to inhibit it for some time.
I'd add that in addition to the programmability, the FPGAs are great if you've got a very narrow algorithm and that is your one hotspot. The challenge is that, if you've got two functions with different algorithms, now you either have to saw your FPGA in half, or you have to somehow on the fly reprogram it in between the different function calls. So the places where it works well, but for like a general HPC multi-physics code, there's both, as he mentioned, a programmability problem as well as a programming problem. You just can't change the program.
Yeah, I only mention it because we're, in our tracking of the market, we're seeing a fair upsurge in demand for FPGAs today.
I maybe should say something. With power systems, we've done a lot of integration with FPGAs, and the places we're doing that is, we had a SQL appliance, right? So somebody in a lab made a SQL engine, and then they have an overall application that can then program that engine directly. And so from a data processing perspective, it can be extremely efficient compared to other options, right? As you move data through pipeline stages. So it has its place. HPC may be a little tougher though, right? That was database accelerators. We do compression, decompression, encryptions, and other place if you need a lot of that, right? But yeah, for general purpose programmability, if you got a Fortran loop or whatever, it's kind of tough compared to something like C or CUDA or whatever, right?
Where do you, all of you, see compilers developing into? For somebody like me who codes, it's always a big decision of which vendor to pick because it's largely attributed to, do I learn CUDA, which I had to, or do I use the old Fortran, iFort, or the GCC GNU suite of compilers, or do you see it being abstracted away into these frameworks that NVIDIA, for example, is trying to push, where you essentially only have to learn Python, and then you have these big pre-compiled libraries that can do 80% of your work. So it would be of great interest to me.
I was going to say that's a good question for the people in the room, right? I'm a hardware guy, and we have this AI product that combines a whole bunch of AI frameworks. We got C code, Fortran. I will say we've been transitioning more towards open source GCC or LLVM based compilation techniques instead of proprietary compilers. I think those can be more usable for people, and so we have had. IBM has been transitioning more towards open source compilation frameworks. But beyond that, then it's, You guys still do Intel compiler, right?
We still do. Yeah, we still do the Intel compiler.
So I'll come in on that. I've seen a lot of efficacy with Cocos, Raja, Legion, these frameworks that you're talking about that are encapsulating the parallelism, kind of abstracting it away from the user. There's a lot of effort that's going into it. A lot of attention's going into their performance. So all the knobs that you've been turning in your parallelization strategies, they've been handling it also and addressing it. And their deployment is actually happening in real production codes, not research science codes. We're talking about codes that are running multiple times, thousands of times, different parameter settings, in order to ensure something like a nuclear stockpile type of scenario, neutron transport. They're actually being used. So I think paying attention to these frameworks would be worthwhile. They're going to keep developing, and yeah, I think the labs are doing a great job with it.
I'll agree with everything that's already been said and add that OpenMP5, OpenACC the directives-based approaches continue to evolve and get better. We've already shown with OpenACC that we can compile from single source code, no if-defs, and efficiently target x86 cores or GPUs.